Welcome to part 8. In this video, we are going to see what are the different types of slab modelings available in ETABS. In previous lectures, we have seen how can we model the slab in our ETABS so that there will be no errors and warnings. Now, we have four types of slabs available in our ETABS. First is shell thin, shell thick, membrane, and layered. We will try to demonstrate each shell. First, we will see what is the difference between thin and thick shell. For thin plate, we follow the Kirchhoff application, which neglects the shear deformation. And for thick plate, we follow Mendling and Wisner's, which does account the shear behavior. Now, for detail about these two applications, you can visit online to ResearchGates for more application. There are certain theories and assumptions. Okay. Now we will see in our project, for example, a residential or a commercial building, which types of slabs we are going to use, either a thin plate or a thick plate. Okay. There is a quick example over here. The nominal size of slab used in a residential and commercial building is 100 mm, 115 mm, 125 mm. A maximum up to 300 mm we are using in residential or commercial project. Now, the average span of slab is 1000 mm, 1500 mm. Maximum we can go up to 5000 or maximum beyond that 6000 mm. Okay. I have an example over here. A continuous slab is in a residential building with LX 5 meters and LY 6 meters. The length of shutter span is 5000 mm. Thickness we can calculate by IS 456 L by D ratio. For continuous, we have span divided by 26 into modification factor. Okay, we have worked the slab thickness should be 175 mm. Now I will calculate the bending span divided by 5 or bending span divided by 10. I am getting 1000 mm and 500 mm. Okay. Now what does CSA knowledge base show us? Tell us that when the shear deformation tends to be important, when shell thickness is greater than approximately 1/5 to 1/10 of this span. If my thickness of slab exceed 1/5 or to 1/10 of the slab, then the shear deformation will govern. Now, for our residential building, if 175 mm is my thickness and 5000 mm is the length, if I do span by 5 or span by 10, I am getting as 1000 mm or 500 mm. If my slab thickness exceeds 500 mm, then shear deformation plays an important role. We have to consider the shear deformation. But now, since the thickness is less than 500, we have only 175 mm, shear deformation would not govern. So for that case, we are using thin plate in our residential and commercial building. So okay, I hope that this point made clear कि हमको जब शेल थिन यूज करना हम जब रेसिडेंशियल एंड कमर्शियल प्रोजेक्ट्स करेंगे तो वी विल ओनली कंसिडर द शेल एलिमेंट टू बी थिन फॉर थिक we are using the thick element in while designing the footings. Now suppose I have a 4-story building. The size of the footing come out to be 2 meters by 2 meters. For encountering the punching shear and one-way shear, I am getting a depth of 500 mm. Suppose now if you work out this 2000 divided by minimum is 5. If my span ratio is 1 by 5, so I am getting as 2000 divided by 5, somewhere around 400 mm. If my thickness exceeds 400 mm, then we have to consider the shear deformation. But now we are providing minimum foundation as 500 mm thick. We cannot provide foundation for 200 to 300 mm. 200 to 300 mm thick. It will not suffice in punching and one-way shear. Okay. So we basically provide 500, 600 and 700 depth. So in that case, the ratio of 1 by 5 and 1 by 10 is exceeding. So it is mostly used while designing, the thick plate is mostly used while designing the foundation. Okay. Now there are some points where the sharing may also govern. Sharing may also govern become significant in location of bending stress concentration, where there is a concentration of the bending stress, which occurs near the sudden change in thickness or support condition, and near the opening or re-entrant corner. This re-entrant corners, what is the re-entrant corner? We will see when we are going to cover the IS 1893 code for earthquake resistant structure. In that case, shear thick plate formation shows a better result, because if there is a sudden change in the thickness or there is an opening, there might be a shear deformation. There might be a shear deformation which would be critical than bending. So in that case, if So in that case, thick plates needs to be modeled. The other type of shell we have available is the layered shell. Okay, this shell I use when we have n number of layers. We have n number of layers of slab. For example, I have a layer of steel plate, then I have the concrete layer. Again, I have the steel plate. Again, I have some chemical coated. Then above that, I have the steel plate. There are multiple layers of slab available in one composite slab. We can say in a composite slab, then we have to use this layered shell. A layered shell is also known as a composite laminate, is a thin wall structure having many layers of different orthotropics or optionally isotropic materials stacked on top of each other. As you can see, the bridge bearing over here, we have the steel plate over here, base plate, which is of steel. We have the elastomeric pad, which is a combination of steel and a chemical PTEE, and we have the stainless steel at the top. So we have four to five different materials on this bearing pad. So this can be act as a layered shell. It is a one element with different layers. So in that case, when we are designing this bearing pad, we can consider it as to be layered shell. Okay. It takes the shear, bending and action loads as per the properties of material. Last type of shell we have the membrane and shell. Now we have understand what is the shell. Now how does the shell work? We will see that, and what is the membrane slab. First, we will see the membrane. Load which is applied to membrane object transfers directly to supporting structural objects. Now, suppose this is my slab. I have applied a perpendicular load, perpendicular to the plane load, for example. So this load will directly transfer to this supporting elements. Without the slab does not have any flexural deformation. It will just transfer the load as per the yield line theory, which we have studied in our engineering. Now, the yield line theory, like for example, if it is a two-way slab, it will transfer the loads according to the two-way distribution. If it is a one-way slab, it will transfer the load as per the one-way distribution. Okay. So this is the membrane. Like it will not carry any load. It will just transfer the loads. For example, this I have applied a UDL over here. It will transfer 50% UDL over here and 50% UDL over here as per the one-way distribution. Okay. Now for shell has object have bending stiffness and therefore resist a portion of the load through flexural deformation. For example, this is I have modeled it as the shell element, this slab. So if suppose I have applied some load perpendicular to that plane, it will try to deform this part and absorb some of the load, and the remaining load is transferred according to the stiffness. According to the stiffness of the supporting member, it will transfer the load as per the finite element basis. Okay. It works on the finite element basis and membrane works on the yield line basis. We will see the quick demonstration of shell and membrane in ETABS so that we can get a practical aspect of it. I have made an ETABS in which I have model a quick model which is a 4 by 4 grid and typical dimensions of it for demonstration. Now in this I have modeled the membrane slab of 125 thick and 230 and a beam size of 300 cross 600 with M25 grid. We will see when we model the slab as a membrane element, what is the difference between them, and if we model it as a shell, then what would be the difference? Okay, now I'll just quickly run this model. Okay, so this model has been run. Now I can go to display, show forces and stress diagram, shell stresses and force. Okay, now I have assigned the membrane properties. Now, this is the parameters we have to see. For example, I will say the load cases for dead load. मैं पहले dead load के लिए check करता हूँ. We have components such as F11, F22, F12, and we have the out of plane as one, M11, M22, and M12. We will try to understand what is this F11, F22, and F12, and M11, M22, and M12. I will go to the PPT. I will show here. Yes, just a second. Now, in ETABS, shell or area element has two types of stiffnesses. One is in-plane stiffnesses and refers to F11, F22, and F12. Now, for example, this is my slab. This is the plane of the slab. So this slab have this stiffnesses plane along the plane, in-plane stiffnesses. This is the stiffnesses along this plane, so we can call it as the in-plane stiffness. Suppose this axis is 1, this axis is 2, so we can say it is F11, it is F22, and as you can see over here, F12 is perpendicular to F22 and F11. It is the transverse shear. Okay. Similarly, we have this out of plane stiffness. Out of plane means the perpendicular to the plane. For example, this is my slab and this is the depth direction. Okay, this is the depth direction of this slab. So this depth, which is the out of plane stiffnesses, which will generate the moment. For example, if my axis is 1, this is 1 and this is 2, ये हमारा second axis है, ये हमारा first axis है. So M11 would be the moment about 1 axis and M22 will be the moment about 2 axis. So this is as shown by the CSI. It is the image taken from the CSI knowledge base. Okay. So this is my M11 along the axis 11. This is my axis 2 and this is the moment along M22. Okay, and M12 is the shear transfer shear moment. Okay. So I hope that out of plane and in plane parameters has been clearly understood. Now let's get back to ETABS. Now in ETABS we will see I have applied the dead load. First I will check the in plane F11 direction. You can see over here there are minor it is attracting some of the forces and the stresses has been seen over here. So this constraint, in-plane constraint has been taken when we are aligning the membrane. Okay, similarly F22 भी हम देखेंगे तो यहाँ पे हमको कुछ माइनर से स्ट्रेसेस देखने को मिलेंगे, लेकिन जैसे ही हम आउट ऑफ प्लेन बेंडिंग पे जाते हैं तो the stresses would become zero. It will not take any out of plane load and just transfers this load accordingly to the supporting member. Now the question might arise if it is not taking any load, so why F11, F22 and F12 is taking slab is showing some stresses over here. So in ETABS, we have features that this in-plane loads can be eliminated with diaphragms. That we will see when we are going to see the understand the this in-plane and out-plane loads can be eliminated by diaphragm. That we will see when we are going into the concept of diaphragms. Okay. So for now, we can neglect this in-plane stiffnesses. Only out of plane we have to check because uh, we will check for the vertical as well, lateral load as well. So for the lateral load, in-plane loads has been considered neglected. As you can see over here, it is the stresses in the slab seems to be zero. Only the in-plane load might occur. That too we can eliminate by using the diaphragm theory. That we will see when we are going to study the diaphragms. What are the types of diaphragms and the relation between them. Okay. Now I have created another model with the shell diaphragm. I have already run this for time saving. This is the slab. I will just show you. This is the slab which I have modified as the shell element. 125. The thickness and the sizes are same. Only the difference is membrane and shell. I will just quickly open the dead load. You can see over here the stresses due to the out of plane has been generated as well in this, which was not in membrane part. Okay. So हम देख सकते हैं यहाँ पे shell element में कुछ stresses attract कर रहा है. It will observe some of these stresses and it will distribute to the remaining loads is distribute to the supporting members according to the stiffnesses. Similarly, हम इसको lateral load में भी check कर सकते हैं. This is lateral load में भी it will take some amount of the out of plane loads as well as in plane loads. So I hope that the understanding of shell has been cleared. For the in plane stiffnesses, it can be eliminated with the diaphragm that we will study in upcoming sessions. Okay.